What's up, guys? Welcome back to another video. So, you guys have probably heard of pi. So pi is just the ratio for the circumference to the diameter. And in this video, I'm going to be explaining an alternative circle constant and why it is much, much better. By the way, this whole thing is based off the Tau Manifesto, so go read it if you want more details. Okay, so let's say you're the first person ever to try and find a circle constant. You might think to the definition of a circle, a round shape whose boundary consists of points equidistant from the center. So the obvious choice would have to be the circumference over the radius, right? Because the radius is just the distance from the midpoint to the circumference. And when you calculate it out, it turns out to be 6.28, which, if you've done, like, any math ever, you'll notice is exactly 2 times pi. If you think about it, C over D is an unnatural choice. Think about it. When in math do you ever use diameter? Like, pretty much never. You always use the radius. So why use it for, like, one of the most important constants ever in math? Okay, so let's go with the more natural approach and see where that takes us. If you just start replacing 2 pi with tau, and you'll notice in a bunch of common equations, tau simplifies it, like, a ton. As an example, the common equation, 2 pi r, is the circumference of a circle. This can easily be replaced with tau as tau r. Tau even permeates into the substance of the universe. The definition of Planck's constant, which is, like, important to quantum physicists and string theory and stuff, is h over 2 pi, which can easily be replaced with tau. If you check the description, there's a link to an 18-page PDF that's full of equations that would be made simpler when using tau. Another common place you'll see pi in mathematics is radians. So if you don't know, radians, it's a way of measuring angles, and 1 radian is the length of the radius of the circle around the circle. This means that pi radians is exactly 180 degrees, or halfway around the circle. This means that half pi is a quarter of a circle, and 3/4 of a circle is half of 3 pi. That doesn't make any sense. But if instead you use tau radians is 360 degrees, or a full circle. This makes radians much, much easier. So a quarter of a circle is a quarter of tau. 3/4 of a circle is 3/4 of tau. It makes angles way easier. So, like, 1/300th of a circle would just be 300 or 300th of tau. So tau over 300. And I don't even know what that would be if you use pi. Now that we understand radians, we can go back to equations. So you might be thinking about one specific equation. The area of a circle, which is pi r squared. You might be thinking, there is no 2 pi anywhere. You can't possibly turn it into tau. But there's tau written all over it. So, the equation for a sector of a circle, which is just a pi shape, no pun intended, is a over 2 times r squared. The a is the angle of a sector in radians. So, let's say we want to find the area of a semicircle. Well, a semicircle's angle is half a whole turn, so it would be half tau. Simplify the equation, and you have tau over 2 times r squared, and that simplifies to tau over 4 times r squared. If we try and calculate the full circle with pi, we see 2 pi over 2 times r squared. So the one equation that had a chance of saving pi, it was just a coincidence. It's just a coincidence that happens to be 2 pi over 2. You may be familiar with the circle functions, sine, cosine, and tangent. I'll focus on sine and cosine, because tangent, that's a bit weird. But to explain the sine and cosine function, take a circle and have a point on it travel along the circumference at a steady speed. So sine is just the x-coordinate of the point, and cosine is the y-coordinate. And if you, like, graph it with time as the x-axis, that's how you get the actual function. And since it's traveling around a circle, it repeats. But people would usually say that its period is 2 pi. But as I've shown before, if we just use tau, it would work much better, because halfway through the function is half tau, and a quarter way through the function is quarter tau. It's just much easier. Another point that pi enthusiasts might bring up is Euler's identity. Euler's formula is as follows: e to the I theta equals cosine theta times I sine theta. The details are a bit complicated, but in a geometrical sense, it basically describes the coordinates in a complex plane. So, imagine a circle centered on 0 with radius 1 in the complex plane. This means that the circumference passes through 1, I, -1, and -I. So I is like the y-axis, but in numbers. It's weird, but just go with it. And think back to before when we showed that tau radians around a circle is just a full turn. And theta in Euler's formula is just how far it is around the circle. So if you go tau radians around the circle, you go all the way to 1. And if you go pi radians, or half tau around the circle, you get to -1, which is just halfway around the circle. It just so happens that if you have pi as theta, it simplifies to e to the I pi equals -1. This specific case is called Euler's identity and is considered by many to be the most beautiful formula in all of mathematics. But with the assistance of tau, it can be even more beautiful. If instead of pi, we have tau be theta, and we get e to the I tau equals 1. You don't have to do any of the e to the I pi minus 1 equals 0. It's just 1. This simplifies it even further and is arguably even more beautiful than the traditional Euler's identity. I've worked hard on this video and have tried to make the case as best as I can, but you really should check out the Tau Manifesto. It goes into way more detail and has FAQs and everything. Yeah, it's just really cool. Hope you enjoyed. Bye!